This is the third section of the hyperbolic functions chapter, and we're going to be looking at identities and equations. Now, these do sort of match nicely with the equations and identities, or identities that we know in normal maths. The trigonometry based on a circle, which is sine squared a plus cos squared a is equivalent to 1. Notice how that looks similar to this here for the hyperbolic functions. We also know that sine a plus or minus b is equivalent to sine a cos b plus or minus cos a sine b. So again, look at the similarities, look at the differences that we have here. And then cos a plus or minus b, this is cos a cos b minus plus sine a sine b. So again, there are some similarities. So we've got over here these three identities based on the hyperbolic functions, which we can use or which we may be asked to prove. So whenever we're asked to prove these identities, we're going to prove it from the definitions of cosh and sine or tanh. So we know that cosh, if I use x, is e to the x plus e to the minus x over 2, and sine x is equal to e to the x minus e to the minus x over 2. So we're going to use these definitions, and we should end up with 1 if we do it correctly. So cosh squared, using the letter a rather than x, is going to be e to the a plus e to the minus a over, sorry, minus a, not x, made a mistake straight away, all squared, so that's like the cosh squared part, and there, minus e to the a minus e to the minus a over 2, all squared. Right, now if we're going to square that, the bottom is going to become 4, and the top, well, we need to basically times the denominator, sorry, the numerator by itself. So basically like e to the a plus e to the minus a times by itself, like this. I might do this over here. I'm going to try and do it in my head. That's going to be for the first fraction, multiplying that out. We also need to do the same for the numerator of the other fraction, which is going to be this times itself. So we need to square that. So let's multiply these out and see what we get. Right, put the arrows in. That times that, that times that, that times that, that times that. Right, so we will get e to the a times e to the a, which is e to the 2a. Then we'll have e to the a times by e to the minus a. So you end up with e to the 0, which is 1. You'll get the same when you multiply the other two. So you'll get 1 plus 1, which is 2. And then e to the negative a times e to the negative a is going to be plus e to the negative 2a. So negative a minus a. We're going to do the same down here. Now, the terms are going to be the same. It's just going to be the signs are going to be different. So e to the a times e to the a, e to the 2a. Then we're going to have minus 1 minus another 1, so minus 2, and then plus e to the negative 2a. So you can see the only difference is one has plus 2, one has minus 2. So let's stick that in over here. So the first fraction will become, once we square it, e to the 2a plus 2 plus e to the minus 2a over 4, because we're squaring top and the bottom, minus e to the 2a minus 2 plus e to the minus 2a over 4. Now they're over the same denominator, so I really should use these identity signs rather than equals, because these are true for all values of a. So that would be e to the 2a plus 2 plus e to the minus 2a. Now we need to be careful here. Minus e to the 2a. Actually, let's put it in brackets. Minus 2 plus e to the minus 2a, like that. All over 4. Now what happens at the top? Well, that and that will cancel out. Then you'll have 2 plus 2, so you're going to get that's going to give you 4, and then the e to the minus 2a's, they cancel out as well. So all you're left with is 4 over 4, which is 1. And since this is true for all values of a, we've just proved it. Yeah, that always equals 1. That identity is true. Okay, so we're going to prove this in the same way that we did the last one. So let's just write down our definition, shine, and I'll use the letter A since they've got, no, I'll use x, is e to the x minus e to the minus x over 2, and cosh x is e to the x plus e to the minus x over 2. Right, so this is just basically starting off with this side. Always start with the side which looks a bit more complicated, and then we can then move to get this. So shine A will be e to the a minus e to the minus a over 2. Cosh B would be e to the b plus e to the minus b over 2, plus cosh A e to the a plus e to the minus a over 2 times by shine B e to the b minus e to the minus b over 2. Right, okay, so we're going to multiply out the brackets. So I'll have e to the ab, then I'll have plus e to the a minus b. So basically I'm doing these two, then I'm doing these two, then I'm doing these two, and then I'm doing these two. So that's the order that I'm doing in case you're wondering. Yeah, so e to the a minus b, then the next one will be minus e to the negative a plus b, and then the last one will be minus again e to the negative a negative b all over 4. Then the second bracket, when I multiply them out, so let me just put the arrows in again so that we're clear about what I'm doing, so you don't lose track of what I'm doing, is e to the ab. Oh, did I put times? Sorry, I meant plus. We're adding them, aren't we? So that should be a big plus sign there. So yeah, e to the a plus b. Then the next one will be negative e to the a minus b. Then I'll have plus e to the negative a plus b. And the last one will be negative e to the negative a minus b all over 4. So that's basically everything over 4. Now what I'm going to do, I'm going to put together the things which are the same, and I've just noticed actually that should be a plus b, sorry, a plus b there, not a times b. Right, so I'm going to put together, I'm going to write sort of that and this, put them right next to each other. So e to the a So e to the a plus b. Have I got any other things which are the same? I've got e to the a minus b. I've got another e to the a minus b. So that's that and that. Oh, that's a negative there. I'll be careful. That's a negative from the second one. Then I've got negative a to the negative a plus b plus e to the negative a plus b. That's this one and this one. Then the last one, I have negative e to the negative a minus b, negative e to the negative a minus b, and all of that is over 4. Now you can see there's loads of stuff there, but things are going to simplify. What do I get? I get 2 lots of this, the first 2. The second 2 cancel out. The next 2 cancel out. And then I'm left with negative 2 lots of, I can write like this, negative a plus b all over 4. I can divide everything by 2, so I end up with e to the a plus b. I'm just going to put it in brackets. Minus e to the negative a plus b over 2. Now if you compare that with the original definition for shine up here, x has been replaced with a plus b. So this is equivalent to shine of a plus b. So we've proved it as they want, just a couple of little errors along the way, so make sure you don't make those mistakes. Right, this is a double angle. Again, in your normal maths lessons you will learn for trigonometry these identities. Yeah, I'll put the sign first. So sine 2a is 2 sine a cos a, and the other one you'll learn is cos 2a is cos squared a minus sine squared a. And again, we're going to be using the definitions, and we're going to start with this side. So this becomes 1 plus 2 lots of, now if it's shine squared, that means we're timesing this, sorry, not x, e to the a minus e to the minus a by itself over 2. Yeah, so e to the a minus e to the minus a over 2. So let's multiply that out. So you get 1 plus 2 lots of, now this is all going to be over 4. So e to the a times e to the negative a becomes 1 when I multiply. Well, actually, let's start with the other term first. E to the a times e to the a. E to the 2a. Then we'll go on to the second one. E to the a times negative e to the negative a becomes negative 1 because the powers cancel out. Then we'll go on to these two. So that's going to be negative, whatever it works out to be. And again, that becomes negative 1 as well. And then the last term is going to become plus e to the negative 2a. So let's simplify that. So we'll have 1 plus, now the 2 at the front and the 4 can cancel down, just leaving 2 at the bottom. And at the top I will have e to the 2a minus 2 plus e to the negative 2a. I'm going to split it up and put the 2 elsewhere. So I've got 1 plus, so I can write it as negative 2 over 2 plus 2 over e to the 2a plus e to the negative 2a. So I've just taken that 2 out, and what will happen is that will cancel out because it's basically 1 minus 1. So I'm left with e to the 2a plus e to the negative 2a over 2. And if you compare it for the definition for shine, that is, sorry, not shine, cosh. This is cosh 2a when we compare it with the definition. Now, rather than work out all of these identities from scratch, which you could be asked to do, there is something called Osbourne's rule. Now, Osbourne's rule works like this. You take a normal trig identity and you replace anywhere you see cos, you put cosh. Anywhere you see sine, you put shine. Okay, so you just stick h's in. But the only difference is if you see a product or implied product of sine, you put a minus in. So for example, if I saw sine x, sine y, okay, well I can put shine x, shine y, but I need to put a negative here if that was a plus, because this bit here is a product of sine. Okay, if I had something like negative sine squared a, I would replace that with shine squared a, but it's a product of sine, so I reverse the sign and this would become positive. Yeah. Now you can even have an implied product. Well, now what do I mean by that? Tan is sine over cos, so there is a hidden tan sine in there. So that means something like tan squared, as you can see above, would be sine squared over cos squared. So here is my product of sine, which means I also need to apply Osbourne's rule. So for example, if I had something like cosh a tan squared a, okay, then using Osbourne's rule, I'm not cosh, cos. So if I had cos a, getting ahead of myself, cos a, that will become cosh a at tan squared a, but in this tan is hidden a product of sine, yeah, from what we've done up there. So this would have to have a negative sign. So this easily allows us to convert between a normal trig identity to one of these hyperbolic identities. Write down a hyperbolic identity relating to, so we just apply Osbourne's rule if we need to. So, oh well, we do need to. So first of all, let's just replace cos with cosh. Now, do I have any product or implied product of sine? No, so that stays as it is. Second one, we replace tan with tan, like this. That's step number one. And then once we've done that, we see, do we have a product of sine or an implied product of sine? Yes, we have an implied product of sine here, because this is sine or shine a over cosh a times by shine b over cosh b. So there's an implied product of sine here. So that means that this plus sign becomes a minus, a very quick way of finding these new identities. Right, we've been given shine x is 3/4. And then what we can do is we can use a trig identity to work out either cosh or tan or shine 2x. So what we're looking for in part A is an identity that links shine with cosh. Now, if we remember our normal trig identity, sine squared x plus cos squared x is 1. I'll just put that here. Then using Osbourne's rule, the cosh identity will be cosh squared x, let's make that squared, cosh squared x minus sine squared. Remember, when you've got a product of sine or an implied product of sine, you make it a negative. So we can use that, cosh squared x minus sine squared x is 1 to help us answer part A. So what does that mean? Cosh squared x minus basically 3/4 squared is 1. So that means cosh squared x equals or is equivalent to 1 plus 3/4 squared, which is 9/16. So that is, well, that's like 16/16 plus 9/16, which is 25/16. Now we need to square root it, so cosh, strictly speaking, that will be plus or minus the square root of 25/16. But we need to think about the graph of cosh, and the graph of cosh, you'll know, is never negative. It's like U-shape thing, so it's like this, isn't it? Okay, so cosh can never be negative, so that means we just take the positive square root. So cosh x is going to equal the positive square root of 25/16, which is 5/4. Right, part B. So we're looking for an identity that links tan with shine, or tanh with shine, and that's only going to be the tanh is shine over cosh. Now, assuming we've worked out part A right, then tanh is going to be shine, which is 3/4, divided by cosh, so divided by 5/4, so that's the same as 3/4, times by 4/5. 4's cancel out, so that just leaves us with 3/5 for that one. So just highlight the answers here: 5/4 for A, 3/5 for B. And then in part C, this will be a double angle. So remember, we'll start with the double angle for sine. Sine 2A is 2 sine A cos A, or x. Now there is no product of sine, so we don't need to change the sign of sine. So we end up with sine 2A, or 2x, is equivalent to 2 sine A cos A. Right, so sine 2x is 2 sine x cos x. So that's 2 times, now shine is 3/4, and cosh is 5/4, again assuming that we've worked it out right. So that will give me 2 times 3, 6 times by 5, 30/16, which I can simplify by dividing everything by 2 to give me 15/8. Here we are trying to solve an equation. Now the way that we solve hyperbolic equations is we're going to replace sine and cosh with their exponential definitions. So there's no cast diagram or anything like that. These are exponentials here. So we change it to 6 sine x, which is going to be e to the x minus e to the minus x over 2, minus 2 cos x e to the x plus e to the minus x over 2 equals 7. And this is basically just about solving this. It says for real values of x, so we shouldn't have any complex solutions to this. So if I times the first fraction by 6, I will get 3e to the x minus 3e to the minus x. Then the second fraction, if I times it by negative 2, then there's a negative 2 at the bottom. They'll cancel out, so I'll just end up with negative e to the x minus e to the minus x equals 7. So have we got bits that go together? Yes. So 3e to the x here, take away the e to the x, leaves me with 2e to the x, and I've got minus 3e to the x minus another one, so that's going to be minus 4e to the minus x equals 7. Now we know the trick for solving these is to multiply everything through by e to the x, so we end up with 2e to the 2x minus 4 equals 7e to the x. So we'll bring it over because this is basically a quadratic. 2e to the 2x minus 7e to the x minus 4 equals 0. Now if you like, you could say at this point let y equal e to the x, so your equation would become 2y squared minus 7y minus 4 equals 0. Now, does this factorize? I suppose I'll give it a try. So I'll do 2 times negative 4 gives me negative 8. Two numbers that multiply to give me negative 8 and add to give me, so times to give me negative 8 and add to give me negative 7. That's going to be, it's going to be 8 and 1, isn't it? So negative 8 and plus 1. So this is the old-fashioned way. So I'm going to have 2y minus 8, 2y plus 1. Now I simplify it down. You may or may not have seen this method. So this gives me y minus 4 in the first bracket and 2y plus 1 in the second bracket. So this is what it factorizes to. So that means that since I've made y e to the x, that means e to the x either equals 4 or I've got 2e to the x plus 1 equals 0, which means that e to the x equals minus a half. So to find my solutions, I need to do the log of both sides. So from here, I'll have log of 4 will give me x, so that's one solution. Now over here, if I try and do that, if I do the natural log of negative a half, remember we can't do the log of a negative number, yeah, or even 0. We can positive numbers, even decimals, but not negative. So actually we're just left with one solution, which is log 4 equals x, or x equals log 4. That's our solution. Okay, so this one here, we can't solve anything that's like a mixture like this unless we can factorize it, because you've got cos squared and you've got sine. So we're going to have to use an identity either to change the sine to cos or the cos to sine, and we can change the cos to sine because if we remember that sine squared x plus cos squared x is 1. The hyperbolic identity is cosh squared x minus sine squared x is 1. So we can use that. That basically means that cosh squared x is equivalent to 1 plus sine squared x. So that's the replacement we're going to make. So 2 cosh squared x minus 5 sine squared x equals 5 is going to become 2 lots of 1 plus sine squared x minus 5 sine squared x equals 5. So here we go. We've got basically a quadratic in terms of sine. So we'll have 2 plus 2 sine squared x minus 5 sine x equals 5. Let's make it look more like a quadratic. So we'll have 2 sine squared x. Then we'll have minus 5 sine x. Now we've got 2 and we're taking away 5, minus 3 equals 0. Okay, now we could try to factorize it. So we can try, or we could just go straight to the quadratic equation actually and get solutions. And I could, if I wanted to, like I did on the previous one, say let y equal sine x or whatever. But I'm just going to go straight and multiply the first and last number, which gives me negative 6. I'm looking for two numbers that multiply to give me negative 6 and add to give me negative 5, which I can do. So the two numbers would be negative 6 and plus 1. So I start by writing, as I said, this is this method you may or may not have seen. So I'll start by writing 2 sine x minus 6, 2 sine x plus 1. Then I cancel down, this can be divided by 2, so I get sine x minus 3 and 2 sine x plus 1 equals 0. So what do I get from this bracket here? Well, I'm going to get sine x equals 3, and from this bracket I'm going to get it's basically 2 sine x plus 1 equals 0, which means that sine x equals, that's going to be negative a half again, like the previous one. Now what I'm going to do from here, I'm going to use the definition for arcsine, and I'll write that here, and I'm going to do the arcsine to both sides. So AR sine x, and this is in the formula book, and definition in it's log x plus square root x squared plus 1. Okay, so if I do, let's take the first one, let's take this here, okay, and let's do arcsine to both sides. So I've got sine x equals 3, so I'll do arcsine to this side, I'll do arcsine to this side, basically the inverse. So that will give me x equals log 3 plus 3 squared plus 1. Yeah, so can you see what you do? Basically, if you do the arc in sine, or basically the sine inverse, basically that's the log x plus square root x plus 1. So that will give us x equals log, now we'll have 3 plus root 10. 3 plus root 10, that's the exact value. Okay, now for the other one, which was sine x equals negative a half. Now sine x can be negative because that does go below the arc, the axis. So we'll do arc of both sides, the arc sine. So we'll end up with x equals log, and it will be negative a half plus the square root of negative a half squared, run out of space here, plus 1. Now if I do that, I will get log negative a half, and then I've got negative a half squared, which is a quarter. So I've got a quarter plus 1, which is 5 over 4, so plus root 5 over 4, which I suppose you could write as root 5 over 2, and there's our second solution. Yeah, so notice how we solve this in a slightly different way to the last one. The last one, there was no squared in it. There was no cosh squared or sine squared, and it was all sine, so we used the definition e to the x. In this one, we had to make that substitution, and we made this substitution up here, and then from there we didn't actually change it for the definitions of e to the x. What we did was actually did the sine inverse. That's actually easier than using the definitions of e to the x. You're just going to be loads and multiplying out. You would end up with the same answer, but it's easier to use the inverses, the arc sine, arc cosh, or arc tang. Okay, so on this one, I can see I've got 2x there and x here, so I can't use the definition for in terms of e to the x. Just like you would with a normal trig equation, we need to make a substitution, and if it was a normal trig equation, you would make one of these three substitutions. Either this, or this, or this. Now we are going to use this one when we apply Osbourne's rule, because then we'll get a nice little quadratic all in terms of cosh. So using Osbourne's rule, we will get cosh 2x is equivalent to 2 cosh squared x minus 1, and that can get put straight in. We don't need to reverse any signs. So what will that become? Well, the cosh 2x will become, well, let's write it down, cosh 2x minus 5 cosh x plus 4 equals 0. So that will get changed to 2 cosh squared x minus 1 minus 5 cosh x plus 4 equals 0. So that's 2, let's make it look like quadratic, minus 5 cosh x, and then plus 4 minus 1 is plus 3 equals 0. So let's factorize that. Now I could probably do this manually, I think, because there must be a 2 cosh here, and there must be a cosh here. Because I've got a plus 3 and a negative in the middle, these are both negative. The two numbers must be 3 and 1. And to make this work, I need the 3 here and the 1 here. So for the first bracket, I get cosh x equals 1. And from this bracket, I'll get cosh x equals 3 over 2. Right, let's deal with this one first. So what we're going to do, they get pumped into the arc cosh formula, because we're going to do arc cosh to both sides, which is the log of x plus the square root of x squared minus 1. So that should be easy enough. So if we do that, that will give us x equals log, and then we just put 1's in here, 1 plus the square root of 1 squared minus 1. Well, that just gives us a value of x of log 1, and log 1 is 0. You can check it on your calculator. So x is 0 is one solution. Now let's have a look at this one here. Now when we did our definition for our cosh and we went through it, we actually had a plus and minus here to start with, and then we took the minus away because we said, okay, that causes a problem because the graph of arc cosh doesn't go below the axis. You'll remember that the graph of arc cosh, okay, let's draw it here, looks like this. Yeah, something like that. It's actually going up, and this is the number 1 here. So x can't be smaller than 1, and that's not a problem because we've actually got 1 as a value of x, so we've got 0 for a value of x in here, so that's not a problem. But yeah, we said we don't put a minus sign in here because it's going to cause issues. Yeah, because we don't want the graph is not allowed to go below the axis. That's not defined. That's only an issue if the value of x is less than 1. Yeah, if the value of x is less than 1, then that's when the problem occurs. But if the value of x is greater than 1, we can include that negative sign. So this negative sign can go in when x, or cosh x, I should say, is greater than 1. Yeah, so just remember that there are occasions where we have the plus and the minus. So we'll do the same over here. If we do the arc cosh to both sides, we'll end up with x equals the log of 3 over 2 plus or minus the square root of 3 over 2 all squared minus 1. So we can work that out. So that'll be x equals log. So underneath the square root, we will have 9 over 4. Take away 1, which is like taking off 4 over 4. So we'll end up with 5 over 4. So we'll have 3 over 2 plus or minus the square root of 5 over 4, which we could write as root 5 over 2. So here's our second solution. So it is possible, if you're not careful, to miss out that second solution there. So just remember, if your value of cosh x is greater than 1, then that is not an issue. Yeah. Right, you should now be able to do exercise 6C on pages 128 to 129. So the rules are there. Osbourne's rule is there as well. It might actually be worth writing down our definitions for sine x and cosh x, which are these, and also arc sine x and arc cos x, and then also that little thing that we need to remember as well. So arc sine x log x plus square root x squared plus 1, and then arc, no c, oh yes there is a c, arc cosh x is log x plus, now I'll put the minus in a moment, but I'm going to put that little thing and we need to remember, x squared minus 1. So we can have the minus as well, and we only have the minus if cosh x is greater than 1. Yeah,